So first, quick reminder, so mean value theorem is another of the three theorems, or value theorems, that prove the existence of a point that meets some condition. Okay, so in this case, we are looking for the existence of a point inside an interval, not at the endpoints. We have an open interval right here. Okay, where the instantaneous rate of change is equal to the average rate of change. So conceptually, that's what that means. Or we could also say the derivative is equal to the difference quotient, or the slope between the two endpoints. Or graphically, we can say the slope of the tangent line is equal to the slope of the secant line. So however it's presented, we can draw that conclusion. This does not tell us where that happens. It just tells us that it has to happen. Okay. We have steps for using the mean value theorem. First, we do need to check the conditions. Is it continuous on the closed interval? And is it differentiable on the open interval? Remember that a lot of times you might just be given that a function is differentiable on a whole interval, or might just say differentiable, meaning everywhere. If it is differentiable, then it is also continuous. Okay. And then we find the average rate of change between our two endpoints, and then we draw our conclusion in the context of the problem. Okay. And then we haven't seen one of these yet, but we'll do one of these. So I'm going to jump around a little bit. I'll come back to Rolle's theorem here in a second. So let's look at this one. It says a test plane flies in a straight line, positive velocity. Okay, so this is a rate function in miles per minute, where it's differentiable. Selected values are shown in the table. All right, based on the values in the table, what is the smallest number of instances at which the acceleration of the plane could equal 0 on the open interval between 0 and 40? All right, we need to justify. So first of all, if it's talking about, can we prove how many times, or the minimum number of times, that a rate, so acceleration is a rate of change of velocity. So can we prove that the rate of change of velocity was equal to 0 over, and basically how many intervals can we prove that for? Okay, so we are already thinking about how a of t is the derivative of velocity. Okay, and we're given velocity values. So if acceleration is my derivative, then I am looking here to say, is there a place where my average rate of change is equal to 0? Because if so, I can guarantee that my instantaneous rate of change must be 0 somewhere on that interval. So when I look at these values, I notice that there's a repeat in the 7, and there's also a repeat in the 2.4. Okay, so that tells me that somewhere between time 0 and time 15, the velocity went from 7 and then up. Now, I don't know how high. I can't say it goes up to 9.5 and then back down, because maybe it goes down and then it comes way up above 9.5 and then it's on its way back down or something like that. I do not know what's happening in between there. But I do know at time 0 and time 15, we've made it back to 7. So the average rate of change between these 2 points, because they have the same value, is going to be 0. All right. And then my mean value theorem will guarantee that I can conclude there must be at least one instance in this interval where the instantaneous rate of change of velocity, meaning acceleration, is also equal to 0. Okay. Why can I do that? I'm looking at the conditions first, and it tells me that velocity is differentiable. Okay, so I'm going to start with that. I'm going to say, since velocity is differentiable and therefore continuous. Remember, it has to be a therefore or thus or so. Some kind of one implies the other, not just both are true. Okay, so it's differentiable and therefore continuous. Okay, and so now I'm going to show the average rate of change on this interval, and then also this one, same discussion as before, is equal to 0. So I'm going to say v of 15 minus v of 0 over 15 minus 0 equals 7 minus 7 over 15, which is 0. Okay, so that's one interval, and 2.4 minus 2.4 over 30 minus 25. So that's the second interval, is also equal to 0. Okay. Then there must be at least, just forgot the t, 2 times in 0 to 40 where acceleration is equal to 0 by the mean value theorem. Okay, so I stated my conditions. It's differentiable, therefore continuous. I used the average rate of change. Now in this case, I did it for both intervals. And then I drew my conclusion in the context where the acceleration has to be equal to 0. And we're going to put a pin in that rate of change of 0 for a second and come back to it. But I want to do one more here. So this one says find the value of c guaranteed by the mean value theorem for this function on this interval. So this is that one extra step. Not are we guaranteeing that there must be a time where the slope or the derivative is equal to the average rate of change, but now we want to know what it is. So we're going to take our derivative, find our average rate of change, set them equal to each other, and figure out what input value makes that true. Okay, so let's do average rate of change first. So the average rate of change is going to be f of 1 minus f of negative 2 over 1 minus negative 2. So f of 1 would be 1 plus 6. So 7 minus f of negative 2 would be negative 8 plus 6 times 4. So 16. Oh, come on, pen. Over 3. So 7 minus 16 over 3 is negative 9 over 3, which is negative 3. So my average rate of change is negative 3. And then I'm going to take, so I know because this function is differentiable and continuous that there has to be at least one time where the derivative is equal to negative 3, but now we're figuring out where that is. So f prime of c, and if you have an x there, it's no big deal. I'm using a c because that's what they've called the variable here. So f prime of c would be 3c squared plus 12c, or again, 3x squared plus 12x is fine. And I'm going to set that equal to negative 3, and then we're going to solve that. So 3c squared plus 12c plus 3 equals 0, divide by 3, c squared plus 4c plus 1 equals 0. And that does not factor, so you can either use quadratic formula or completing the square. So I'm going to use completing the square. So that's 4, and that'd be a minus 3. Okay, so c is equal to negative 2 plus or minus, 3. Yeah. Negative 2 plus or minus root 3. Okay, if I add the 3, take the square root. Okay, and put a plus or minus on it. So here I have two different values, okay, and this is approximately, let's see, what is that, 1.7-ish, so this is going to be around negative 0.3-ish, and positive, let's see, negative 2 minus would be negative 3.7-ish, something around there. Okay, I don't really need to know what the decimals are. I can stop right here, but the reason I'm checking that is because I need to verify that if I have more than one value here, that they are inside this open interval, not at the endpoints, okay, and not outside that interval. So at both of these values, the slope is equal to negative 3, but that doesn't mean that both of them are values guaranteed by the mean value theorem, okay? So this one is outside the interval, so I'm not going to count this. So I only have the negative 2 plus root 3 as my answer. So c is equal to negative 2 plus root 3, and that is my value of c. Okay, and then the last thing is, let's come back up here, is Rolle's theorem. So I didn't include Rolle's theorem when we went through the notes originally. So mean value theorem says, whatever our average rate of change is, there must be a point where, if the conditions are met, where the instantaneous rate of change is equal to that. And then this guy comes along, and I'm sure he made some other great contributions to math. This is not one of them, because what he said, yeah, but what if that average rate of change is 0? I mean, 0 already works with, because mean value theorem works for any average rate of change. And he's like, yeah, but what if it's 0? And I don't know why that's more important or why that's special enough to put his name on it, but he did it. And so Rolle's theorem is the mean value theorem, but specifically when the average rate of change is equal to 0. So Rolle's theorem is when the average rate of change is equal to 0. And then the conclusion is the same. Then there must be an instant, if the conditions are met, where the derivative is equal to 0, okay? Again, I don't know why he gets credit for that when it's not really different from MVT, but he does. Now, I will say the only thing that might make this slightly better is we can save one step in finding our average rate of change, because if the two endpoint values are the same, then the slope is going to be 0. So like when we did this one right here, 7 minus 7 over 15, really I could have just said, because v of 15 equals v of 0, then I know that the difference would be 0. And then I wouldn't have had to write over 15. So I really don't know that that saves very much. On an AP test, you are not going to have a question where you can use Rolle's theorem, but not, the mean value theorem. But you may have one hint on Unit 5 assessments here. So anyway, that's why we're doing it. Oh, gotta go back up here. So anyway, Rolle's theorem is when the average rate of change is 0, which happens when f of b is equal to f of a because your slope is 0. Okay, so if I'm looking at this function here, does Rolle's theorem apply? Well, let's see. G of 2 would be 2 times 4 is 8 minus 6 plus 6 is 8. And then G of negative 1 is 2 times 1, and then plus 3 plus 6, which is not equal to 8, which is 11, and these are not equal, so no, Rolle's does not apply. So what we're looking for with Rolle's theorem that's different from mean value theorem is just, are the two endpoint values the same? Because then the slope would be equal to 0. The mean value theorem does apply. I can still do mean value theorem for this function on this interval. I could find the slope between these two endpoints, so I could do 8 minus 11 divided by 2 minus negative 1, but specifically, is the rate of change 0? No.